Hello, everybody. This is Nina Bassuk. I'm from Cornell University, and I work in a group that deals with growing plants in difficult sites, human impacted, mostly urban, but very difficult sites that have been disturbed by some human activity. And so just to give you a little bit of background, in the summer of 2019, I was asked by the National Park Service to take a look at the Flight 93 memorial landscape because there were some issues there they thought needed some improvement. And so I said, okay, I'll take a look. Went there for a brief review and then came back in October of 2019 to do a full evaluation. So this is the site you're looking at. Of course, we know the terrible day of what happened. Flight 93 took off from Newark and was headed for San Francisco, but it was turned around to go toward Washington, D.C., and the passengers and crew struggled for control of the plane, and then it crashed in Shanksville, Pennsylvania on 2001, that terrible day. So that very rural site in Shanksville, Pennsylvania, very non-populated area, and the National Park Service decided to create a memorial there to the 40 people who died. So this is the overall site, and basically it's almost 1,000 acres. It's a very large site. And you can see a black outline, perhaps, the entire site that the National Park Service manages. And you can see the flight path of where and the impact of where the crash actually took place. But I want you to focus on the green curved area in the middle of your screen. This represents 40 memorial groves, 40 groves, and each of those groves has 40 trees. So it's 1,600 trees in that curved dark green area. Those memorial groves, and they were planted in 2012. So this was the area that the National Park Service wanted us to take a look at because there are issues with the trees. So again, it was 1,600 trees, 40 groves of 40 trees. So let's take a look. So first of all, I want to mention that what we do when we go to some of these sites that need to be looked at, we do a site assessment. We have to understand what the opportunities and limitations of the site are. So we're going to the site with that idea in mind. So when we get to the site, this is some of the 40 groves. These were the really good ones. So there are trees. This was October, early October in 2019. So there's a little bit of fall color, but this is a look at some of the trees. But this was a look at a lot of the other trees. So there were some that were decent, good, I would say, possibly. And some that were dead, and some that were dying, and some that were in really bad shape. So it was really striking to us. We evaluated every single tree of the 1,600s, and we took soil samples to evaluate what was going on underground. So this is some of the sites which basically had no live trees. Again, they were planted all at the same time, same year at least, and I don't think that was the issue in terms of the timing. So we had ratings for each of the trees, and there's me, and this tree would be considered a good rating. I mean, it's not great form or anything like that, but it still would be considered a good rating. This would be a moderate rating. Obviously, a lot of dieback and poor form, and here we would have a fair rating, which is a lot of dead, again, poor form, poor growth, and we have a poor or dead rating. So these were the ratings we used to evaluate the trees, as well as taking the species different. We had to identify all the species that were there too. We had gotten some information from the National Park Service about what people thought were the species, but that turned out not to be wholly accurate. Some of the other things we saw, this is a red oak gall. It looked like the size of tennis balls and enormous galls on some of the scarlet oaks that were there. We saw these small galls. You see, these are the white oak galls. So a lot of these trees, although they might have looked okay, they had a lot of insect infestation. We saw on the ground, we saw sedges, which indicate really poorly draining sites. These are not planted, these were sedges, not grasses, that indicate poorly draining soils. We also saw lichens on many of the trees, which indicate really slow growth, because lichens are basically are sloughed off when trunks are growing and becoming larger. But if the lichens are staying there, then means the growth is not very rapid. And we also saw a lot of deer rub damage. Here, as you can see, where the deer had rubbed the trunk, and it's trying to close over after that. We saw a lot of deer damage on these plants. And we saw poor staking. So it's a very windy site, which we noticed when we were there. And there's some, and these are small trees that were planted. So there's an indication that people tried to do staking, but this was not a good staking method. And many times the stakes are just out of the ground, as you see here. So here's a picture, a graphic of all the 1,600 trees. Each dot is a tree, and you can see, and the color coding denotes the condition of the tree. So from good, moderate, fair, poor, dead, or missing. The purple is missing. So as you can see, there's a gradient from good to moderate, fair, and poor as you go along the crescent of these plantings, which is interesting to us. Although even in the good area, the darker green, you see quite a few missing, some dead, some really poor condition. But there were several at the top of that crescent that were pretty good. But as you go along, the 40 groves, it gets worse and worse as you walk along that almost 2 miles of groves. So after we did initial tree sampling, and I'll tell you more about the species we found there, we also got a backhoe to do some soil evaluations. So we had 6 areas where we took 2 samples at each location. One was at the top part of the soil, and then one we went deeper, about 24 to 36 inches deep, to get a lower volume of soil to test, to bring back to Cornell to run through our soil sampling tests. Some of the things we noticed, though, let's see this. So there's our backhoe. It wasn't possible to put a shovel in the ground, by the way, in these sites. They were very, very compacted. We tried to do some simple compaction tests, but it was virtually impossible to really get a shovel in the ground. So we used the backhoe, which is always very useful in this situation. And one of the things we saw for these clods, when we started to dig just the surface, we saw clods, meaning telling us very poorly structured soil with no crumbs. We have big clods of soil. And as you see here, this has soil with no structure, no aggregates. And this is what we want to see. Of course, we didn't have that, but this is what we would like to see. And then we would actually get it deeper, and we saw coal. So this was an abandoned strip mine, coal strip mine site, and which would mean surface mining of coal. And when we started to get down past 12 inches, there was plenty of coal still in the ground. And this was worrying. This was kind of condition that would be very unusual for 1,600 trees to be planted in a coal mine. But that's what we saw, and the effect of the coal, not just being difficult for plants to grow around, has a chemical effect as well, which we found out later. So this was an abandoned strip mine. There had been no soil remediation before the trees were planted, and the result was as we found. We also, when we had these big pits opened, we also wanted to do a percolation test to see how water drained. And the soil was heavy, a sort of heavy silty loam or clay, but there were lots of coal in it. And I thought, well, it might drain because of all the rocks and the coal in the soil. But we filled these pits up and we went away for an hour. We came back and there was virtually no drainage, no perk down. So we filled them up and they stayed filled up even after an hour, which you would expect to see a little bit of movement, but there was none. So this was another major issue which we had to deal with. And this is a simple test we would do looking at inches per hour. And again, with that big pit, we had no percolation. So just let me tell you about some of the trees we found there. So there were 2 maples. There was a red maple and a sugar maple. And you can see that the red maple on the left, about 35% of those red maples were in pretty good condition. And that you would note, I mean, basically red maples can deal with poor drainage, and that would be, basically looking at that issue. And with the sugar maple, however, they do not like poor drainage, and only 12% of the sugar maples were in good condition. So we're talking about a lot of trees here, and beyond that 33% with red maples and 18% with sugar maples, all the remaining trees were unacceptable in terms of their growth. So a lot of really poorly looking trees. And this was the best instance. So we had several oaks as well. We had chestnut oak, a few more of those. They had 24% good. The black oak had virtually no good trees. So they really did poorly. And then the most numerous group were the white oak, Quercus alba, and the scarlet oak, Quercus coccinea. And both of them had about 30% good, and the rest of them unacceptable. So we're dealing with a lot of trees out of that 1,600 that were considered unacceptable. And this is considering this is 7 years of growth. So they were planted in 2012. We looked at them in 2019. So it's a lot of years of growth to have such poor results. So all the trees combined, 407 were good, and all the rest, 1,200 or so, were poor, dead, missing, or unacceptable growth. So now we look at the trees. It's pretty depressing, quite honestly. But we thought there was major issues here with how the trees were being handled on site. And a number of people at the Park Service said, well, it's just species. We had to have better species. Well, my experience is that species is important, but soil, basically is the most important thing. You can have the best trees in the world, but if you have poor soil, that really overcomes any kind of species issue. So we wanted to look at the soil in a very detailed way. And the Cornell has a soil health test, which looks at both the physical, the chemical, and the biological aspects of soil. Now, often when we take soil samples, what we're really looking at is the chemical. What are the nutrients, maybe the pH, but we're not looking at the physical and the biological, which is equally, if not more important than just the chemical aspect. So we're looking in the physical, structural stability, aeration, storage, physical root proliferation, ability to do that, the structure of the soil, the crumbs or peds or clods. In terms of the biological, we're looking at potential disease issues, organic matter decomposition, mineralization, pest suppression, and in chemical, we're actually looking at nutrient storage and pH. So there are all of these aspects are important in terms of evaluating the soil on a site, especially this large site that we're dealing with. This is the soil health test. It does we took soil samples, large soil samples, that have them run through all these different tests that we decided were important. So this is just, I'm going to show you one of the 12 samples. This is one soil sample. You can see on the left, you have the three colors, the purple, the green, and the yellow. The purple are the physical aspects of the soil. And the column in the middle is kind of stoplight colors. You know, red is stop, yellow is moderate, and green is good. So looking just at the colors, we had pretty good water holding capacity, 21%, which is pretty good. But we had exceptional surface hardness of the soil and subsurface hardness going down deeper. So we had basically no way for roots to proliferate in that soil because the soil was rock-like. Also the aggregate stability, that's the crumbs or PEDs, the aggregate of the soil, we had very, very poor aggregate stability. So we had those, what we saw in the field with those clods, but no tilth or PEDs or crumbs that we would like to see. When we come to the biological aspects, we had poor organic matter, only 3%, and then we had soil protein, and which basically is a proxy for biological microorganisms that are mineralizing nitrogen. We had pretty high root pathogen pressure, and we actually grew beans in the soil, and we looked at the roots and saw whether there had been some fungal problems there, and there were. Soil respiration is the action of microbial activity, of microbes that are actually breaking down the soil into usable nutrients for plants to grow, and that was very, very poor. So there's very few microorganisms. And active carbon is a fraction of the total organic matter, which is the energy source for the microorganisms. So a portion of the organic matter is actually the food for microorganisms. And that, again, was very poor. When we come to the chemical aspects, well, the soil pH was, in this case, was quite low, 4.9, although we had pHs in the 7s. So the pH or the acidity or alkalinity of the soil was very, very varied from all the different sites we took. But in terms of the phosphorus, potassium, and elements, nutrients there, they weren't bad at all. So if you just took a soil test and looked at the chemical aspects, you might not think the soil was so bad. But when looking at all the different aspects of soil, it really is clear that we had a very, very damaging situation. And the overall quality score for this was very low, of 34 out of 100. Other things we found. Toxic elements, we found heavy metals, barium, chromium, nickel, copper, zinc. These are interesting. We don't see them in high levels in most soils, but because of the strip mine, I think that's why we saw them there. These in themselves are not necessarily toxic to plants, but obviously you don't want to be breathing in the dust or handling this so highly. But the most important thing we saw was highly toxic levels of soluble salts. Now, these aren't de-icing salts, sodium chloride. These are salts created by the action of the coal and the soil and the weathering over time. So we had highly toxic levels of salt to non-saline or lower F. So we're getting very variable, but there were at least half of the sites had highly or strongly saline soil in the soil solution. So that was very worrying because that's something that can really kill trees pretty quickly. So how do we deal with this? We get all this information, the soils, the trees, and there's several things we can do. Well, we could have protected soil structure during construction. Well, that bird had flown. We couldn't do anything about that. We needed to think about how much volume we would need to remediate to allow trees to grow. We could replace the soil, but that seemed to be, out of the budget of anybody in that area. We could amend the soil, but that's, there's something we could talk about. We could bury the soil, actually bring better soil on top and plant into that. And of course, appropriate plant selection is still going to be an important aspect of dealing with compacted soil. So building on top or creating mounds with good soil is one way to deal with not having to deal with very compacted soil and poor soil underneath. that didn't seem to be a reasonable aspect in this particular grove model. We could have blended soils and brought new soils in, a very expensive, very enormous amount would have to be blended to create a soil that would be good for plant growth. So this didn't seem to be a reasonable aspect potential either. So we're basically left with, we have to think about the volume we need. We have to amend the soil, decompact, and dilute. When you have highly toxic elements in the soil, dilution is your best aspect, but we also had to decompact because of the dense nature of the soil. And we had to think about appropriate plant selection. So these were the ways that we wanted to go. So one of the things I'm going to tell you about is a method we've been working on for 20 years and have a lot of research based on this. It's called the very literal scoop and dump method of soil remediation using a backhoe on site. So what is the scoop and dump method? So we generally apply a thick layer of compost, 6 to 8 inches of compost on the top of a compacted soil. And using a backhoe bucket, we dig down to at least 18 inches into the soil, and the bucket is lifted with the topsoil and compost and 3 feet in the air and dumped down onto the ground. The soil compost mixes. Then it's a kind of, you get veins of compost into this compacted soil, this cloddy soil. Then we would plant directly into that and surface mulch every year to replenish organic matter. We're adding a lot of organic matter. 6 to 8 inches out of 18 inches is more like a third or more by volume of compost into this compacted soil. This is one of the sites we did on Cornell campus, which you see after construction. The soil was basically like concrete, and we performed this method. I'm going to show you a short video, hopefully here, which will allow us to see what it's like.
This is a production of Cornell University.
You notice that the soil is still very rough. We didn't smooth it out or rototill it. We're just putting the plants into that remediated soil. It's always great to have 40 students doing this kind of work. So this was initially in April of 2014. We'll show you what happens over a few years. This is the end of planting in May of 2014. September now. Plants are growing. We aim for something called canopy closure, which is the canopies of the shrubs and trees touching each other, so we have very little weed invasion. But this is not in anywhere near canopy closure. So you see the runoff from the parking lots going into these bioswales. This is July of 2015. We're seeing a lot more growth. We're getting near canopy closure in some aspects. And this is 2 years after planting. We're really at canopy closure. We have very little weed integration. We have some weeds on the edge where the asphalt is, but basically the plants are pretty well knitted together and are growing really well. I mean, really good growth, having been in a very compacted soil before that.
This has been a production of Cornell University, on the web at cornell.edu.
So we've used this scoop and dump method for over 20 years with good results, but we actually did a research study on it covering 12 years of this method. And we looked at soils that we had done the scoop and dump and versus those that had not been amended. And we looked at what happened in the soil. We knew the plants were growing well, but the soil was interesting to show. So first we look at aggregate stability, which is that you can see at the bottom, the clods with poor stability. And if the action of rainwater just sort of melts the particles of soil away, which becomes recompacted. And on the right, you see the crumbs or peds of the soil with good structure, which allows water to drain through and roots to grow through. So we were looking at this aspect, and we had very poor, as you remember in that soil results, we had very poor aggregate stability in our test soil. We want to look at these peds or crumbs, basically are the space between them allows for drainage and root growth. So this is a critical aspect of soil that we're always looking for. And you can see in our amended soil for after 13 years, we had really good aggregate stability. And in our unamended, we had very poor aggregate stability, 72% in the amended versus 34% in the unamended. Organic matter is a critical aspect of soil, and we had pretty poor levels of organic matter in our site soils, about 3%. And so this enables to feed the microorganisms and to actually help with dedensifying the soil. So we looked at that scoop and dump you'd expect with adding all this compost. So we had 8% organic matter, which is by weight. So that's really a lot of organic matter versus 3.2 with the unamended, which is very much like our site in Shanksville. We have active carbon, which is the portion of the organic matter. This is actually going to be feeding the microorganisms that are going to be doing the heavy lifting of making these organic matter and minerals available to plants in terms of nutrient availability. So and also in terms of aggregate stability. So this is the portion of the organic matter that's really important to feed those microorganisms. So we had, again, high levels of active carbon and low levels of active carbon in the unamended soils. Water holding capacity wasn't a problem too much. We had 21% available water holding capacity in our test site. But in fact, we did get a little bit more organic water holding capacity with our scoop and dump. It's about 23%, which is very much like the Shanksville site. Potentially mineralizable nitrogen. I'm not going to go through the nitrogen cycle with you, but basically we're looking at moving ammonia to ammonium so that plants can take it up. And that's microorganisms, again, are doing that for us. So potentially mineralizable nitrogen, again, very good with the scoop and dump and very poor with the unamended soil. The surface hardness, we use a field penetrometer to actually push into the soil and get a reading in pounds per square inch. Anything over 300 pounds per square inch means that roots cannot penetrate through it. So it's a measure of the usable depth of plant soil. And so in this case, we had virtually no usable soil in terms of density on the Shanksville site. In our research, we get much more reduction in density with the scoop and dump. Bulk density is another measure of density that we take, and this is just showing a field application where you have denser soil where it's been plowed, and on the right you see more crumbs and peds on the right, so on the far right. So we're looking at the density of the soil. It was very hard to take the density because of all the rocks, but in our research we found that we had a much lower, which is good. We had a lower density in the scoop and dump and a much higher density in the unamended soil. So over time was interesting. So we did this, the results I just showed you was an average of 12 years, but we wanted to see what happened over time from the first year to the 12th year. And this is showing a scoop and dump operation. But what happened over time? My thought was that it would be best at the beginning when you just like de-densify the soil and put in the organic matter and have the lowest density. But in fact, it was much more different than I expected. So here you have at the bottom is the years since our scoop and dump from 0 to 12 years. And you have the density. And what we want with bulk density is lower, not higher. So the lower it goes, the better. It's the least dense. And you can see that over 12 years, we had lower density than we did at the beginning, which was really surprising. And it's showing that the microorganisms in the soil, which we're feeding with this active carbon, are actually creating peds or crumbs, which can actually increase or decrease the density and improve the bulk density. We also saw active carbon, that food source for microorganisms. Over time, we're getting more active carbon based on the way that the compost is being broken down to feed microorganisms. So these are very encouraging results. So amending incorporate at least a third to 50% by volume. So this is not putting in a little sprinkling of compost. You have to provide enough compost to really make a difference in terms of the density. We amend over a site, never amend a hole. At least 18 inches depth. With the Shanksville, we're going to recommend 24 inches depth. And we have to think about excess drainage, whether you choose plants that can tolerate wet soil conditions or provide other kinds of drainage apparatus. So back to Shanksville, we have an idea of what we want to do, and we proposed this to the National Park Service. It has not been done yet since everything came to a halt last year. But we would take one grove, one of the 40 groves with 40 trees, and remove everything which is basically dead to begin with. And then here's our 40 groves, 5 rows of 8 trees each tree 30 feet apart. We'd go down, put 8 inches of compost in a 10-foot wide band of these 240 feet long, basically alleys for trees. We would then take a backhoe, put 8 inches on, and then go down 24 inches. So we're getting a third by volume of compost to soil, 24 inches down, and incorporate compost with the soil at a very high level to dilute some of those toxic elements. We would do this over one entire grove. And we still have the same design location where the trees would be. There's 8 trees in a row, and so it'd be 30 feet apart. And then we would mulch the entire strip, so to increase the organic matter as it gets used up. So the mulch on top actually increases the organic matter down below, as long as you have microorganisms doing all that good work. So we just have to think about plant selection is my last part here. We can choose plants that have fewer diseases or insects. We can choose plants that are different sizes, have heat and cold different abilities to tolerate heat and cold. We can choose plants that can tolerate poor drainage. That's the important thing, because we know even though we're going to amend the soil, we're still going to have poor drainage down below that. And dry soils, yes, you can choose trees that can tolerate dry soils up to a point. pH, yes, you can definitely choose trees that have different abilities to tolerate the acidity or alkalinity of the soil. Salt, somewhat, that's a hard one because we have high saline salts in this spot. But compaction, you cannot choose plants that can tolerate the density that we found there. So here's a few trees that we think might be good. It's not the only ones, but these tolerate. In fact, when we were on the site, we saw black locust everywhere on this National Park Service area. So it's a native of Pennsylvania. It's a plant that fixes its own nitrogen and makes its own nutrients, if you like, in the soil. It tolerates high salts, poor drainage, and drought. So it's one of the possible trees. Honey locust, it's also one that can tolerate poor drainage up to a point and can tolerate some salts, which is another big issue here. Gymnocladus, Diocus, Kentucky coffee tree, another good tough tree for can tolerate some salts and tolerate some poor drainage and drought, and very alkaline and acid soil compatible, so it doesn't have a problem with varying pHs of the soil, as do the other ones, Gladitia or Robinia. And liquid ambar, sweet gum is another possible tree for this site. Great fall color, but it also tolerates some poor drainage. And we'd have to look at make sure that this wasn't planted in a place where the pH was very high. It doesn't tolerate a really high pH, but it tolerates moderate to low pH. So this was another. And then there's several hybrid elms that are resistant to Dutch elm disease and elm yellows that would be really good possible trees for this site. So there's just a few. There may be others. Oh yeah, this is one I thought I'll put in. Pyrus galleriana, which has a very bad reputation because it tends to fall apart and it's invasive. There's a new cultivar called Chastity, cute name, for a sterile form of calorie pear. So this is one we think would be a great addition as well. So proposed actions: amending the soil using scoop and dump. For a test grove of 40 trees, choose at least 4 species to assess growth over 2 to 3 years. Stake and protect trees from deer, damage, and wind. Use 1.5 to 1 3/4 caliper trees, either B&B or container grown, so they're a bit bigger to start with, and may have a better way of getting started, and remulch every year, water as needed, depending on what the season is like. So these are the proposed actions, and I think we'll leave it there as to what we saw. We evaluated, and we're proposing actions to try to remediate this very difficult site.